Hi, so today we are going to study about the recurrence relation. Not exactly recurrence relation. Today we are going to see what is the necessary condition to get a order n time algorithm in a recurrence. So in that scenario, we'll study the median finding algorithm, which is a probabilistic median finding algorithm. Later, I will describe another median finding algorithm, which also finds which is also recursive and also finds the median, but it's a deterministic algorithm, and this one is a median finding algorithm, which is not a deterministic algorithm but a probabilistic algorithm. So it's a very easy algorithm. The only thing that you need to know, okay, I'll come to it later. So basically, first we'll start with a recurrence relation, which you might get in a recursive algorithm. So while doing an analysis of recursive algorithm, so we might get a recurrence relation such as t of n equals to t of c1n plus t of c2n c2n plus order of n if n greater than some n naught, and for some n for n less than equal to n naught some constant c. So what happens is that we can draw a binary tree and do the analysis for this. So let's write order n as n. So we divide it into two parts, that's c1n and c2n. Okay, and this division continues. Okay, so replace n with c1n, we get this as c1 square n, and this as c1 c2n. So basically this way the tree grows, and we can finally say the leaves becoming as order 1, count the number of leaves, which is usually a upper bound on the number of internal nodes of a binary tree, and find out what is the time complexity of this recurrence relation. So basically what we do is, in each step we'll replace tc1n with this equation itself. So basically here we'll replace c1n, and see whatever equation we get here, we'll put that. So basically the order n terms remains, and finally these will turn out to be order 1 in the leaves, and these order n's will come in each part. So basically in each step, whatever we get, c1 plus c2n in this step. Okay, so whatever we get we'll calculate in those levels. Okay, and that will be actually order of n. So basically we'll see what we get. So what our motto, what I wanted to tell is that, suppose we have a n sized array, and suppose this is c1 part of n, c1n, c1 c2 are fractions. Okay, c1n, this is c2n. Okay, and suppose c1 plus c2 is less than 1, then we have some remaining part of n, which is 1 minus c1 plus c2 into n. Okay, this part. Okay, so if we have some conditions such that c1 plus c2 is strictly less than 1, then we are at each step not seeing a part of the array. At each recurrence step we are not looking at a part of the array. In that case Tn turns out to be order of n. You can solve this and check. So in that case Tn turns out to be order of n. So if we are trying to formulate a recursive algorithm which should run in order n time, we need to assure that at each step we are not looking at a part of the array. Okay, so if we are not looking at a significant part of the array, only then we can do a recur algorithm which runs on order n. So basically later on also we'll study a algorithm sorry, later on also we'll study an algorithm of median finding which takes order n time. And today's median finding algorithm is a little bit easier because it's a probabilistic algorithm, so its analysis might be a little difficult for few, but I'll try to break it as easy as possible. Okay, so we'll see that in each case we are not looking at some half of the array, and we are finding out the median even then. So basically at each recurrence step we are eliminating a part of the array. So that's how we get this Tn as an order of n. Basically you can do a geometric series and see this. So r is less than 1, so the first term dominates. So if r is less than 1, right, c1 c2, these terms are r's, okay, squaring up. So if r is less than 1, okay, so only the first term dominates. Okay, so we get order of n. Simple theory. If you did not get, I'm telling one more time. See, this is order n. Okay, order n I have written as n. So this is order of c, replacing order of c1n and order of c2n. So this in next steps become order of c1 square n, order of c1 c2n. So basically this, if this is a fraction, as we go down these terms become smaller and smaller. So if we do a sum, we see that if r less, this is actually a geometric series, and so when we are doing a geometric series, sum of a geometric series, we know that the first term dominates, which is order of n. So it's order of n. This is order of n. Okay, so that's it. So next we directly go into our median finding algorithm. Okay, so so the median finding algorithm. So we have an input array or whatever sequence, input suppose x of n numbers, x1 x2 xn. Okay, so let's the be real numbers, not interested in complex numbers as of now, because we don't usually sort complex numbers anyway. So what our required output is to report the median of these. So what is a median? Median is basically if we sort these n numbers and we have to report the middle element. That's basically the definition of the median. And suppose if there are even number of numbers, we basically do a sum of the middle two elements and report. So basically it's a rank finding question, rank finding question. Okay, we have to find the n by 2th ranked element in this array, n by 2th ranked element. So let's find out. So what our next algorithm will also be finding the second maximum. So here we are finding the first, doing a little difficult one, and then we'll look into the easy one, the second one. Okay, so basically how do we find the median? So basically first let us look at the permutation, which is the sorted permutation of this array. The sorted permutation of this array, let that be this. Okay, let us consider for unanimity that these are Okay, distinct elements. Okay, so suppose the sorted permutation of this array is written as this: a1 a2 an, where a1 is 1 of x1 x2 xn, a2 is similarly. So basically the middle element is here. Okay, so our algorithm is basically to select a good splitter, a good splitter. Okay, the splitter should be among this region. Okay, n by fourth from the middle, and on my fourth from this. So basically if we sort this, we are not sorting it, I'm just saying for the analysis, if we have the sorted array or sorted sequence of these x1 to xn, and we are looking at n by 4 from middle this side and n by 4 from middle this side, this part of the array, the number of elements coming in this part will, if we select a splitter from this part, then we say it is a good splitter. If not, then it's not a good splitter. So basically this is n by 4, this is n by 4, so this is n by 2 part of the array. So n by 2 elements are here in this part. So these n by 2 elements are scattered inside this entire sequence, but they are there. So if we choose one of these n by 2 elements, then we say we have found a good splitter. So basically in the sorted array, if we look into the middle n by 2 elements, where from the middle n by 4 from this side and n by 4 this side, so this is n by 2. So if we get any of these n by 2 elements as our splitter, then we have found a good splitter, else we have not. So these n by 2 elements in the middle are actually scattered inside, and what we'll do is we randomly choose one element as a splitter, and we'll check if this element is within this element. So how do we check that? So basically we'll write x1 and x2 as two halves. So x1 will consist two sets. So x1 is a set of x, of elements of x, such that x belongs to capital X. Okay, and x is strictly less than a, and this is x minus x1. Okay, so basically this is how we write. So here a is our splitter. Select a good splitter a. Okay, so we have to select a good splitter a such that this happens. So we have found a good splitter a if in the sorted array it lies within here. So how can we define this? So the definition of this is if the cardinality of x1 less than 3n by 4 and cardinality of x2 is less than 3n by 4. So basically we also see that since x minus x1 is x2, so cardinality of sum of cardinalities of x1 and x2 is n. So basically what this suggests is that if x1, both cardinality of x1 and x2 is less than 3n by 4, that means the number of numbers which are less than x must be less than a, must be 3n by 4, or the number of numbers which are greater than a must also be less than 3n by 4. Okay, so basically it gives us this region. So basically if x1 is 3n by 4, the number of numbers which is less than 3n a are this 3n by 4 numbers, okay, and 1 by 4 or greater. And if we get a here, then we will get 1n by 4 here, 3n by 4 a here, okay. So basically, and these are the limits of a, and it's given by this if condition, okay. So we get we say a is a good splitter if first we divide x into two parts. So this takes order of n time to check all elements of a x, capital X, and divide it into two sets, x1 and x2, okay. Basically we run through them and see if it belongs to x1, we give them say level 0, level 1, sorry, and if it belongs to x2, we give them, if doesn't belong to x1, we give them level 2. So basically it will take order of n time and will keep a count of number of one of them, number of label of ones while doing this. And if we see that it's less than 3n by 4, okay, and then we have got a good splitter, okay. If both of them is less than 3n by 4, then we have got, sorry, if both of them are less than 3n by 4, then we have got a good splitter. So basically we're looking into n this n by 2 elements. If we get one of them while finding a good splitter, then we are done. So basically we use a randomized function to select one of these elements which will be our splitter, and then we split into two sets, x1 and x2, and check for this condition. This is the condition for good splitter. So basically our algorithm will be pretty simple. While 1, we find a good splitter, a is equal to some random number between number of x, okay. A is a random number of x, okay. A is the random number of x, and okay, and if a is good splitter, then we break, okay, then break, okay. Then we just divide it into two, x1, x2, and if x1, then break, okay, sorry, you can't see here. So after that we divided the x array into two after we got a good splitter, okay, and then check if both halves are equal, we have the number, okay. If both halves are equal, we have the number. If not, then a is the median, sorry. If both halves are equal, we have a as the median. If not, then we basically discard the elements in the small set, because the median will be in the bigger set, obviously. So basically if x1 greater than x2, then discard x2, okay. Then discard x2 in the next iteration and just pass on x1, and in